Okay, thank you very much, Eva. Thank you, Professor Casanor. And we are ready to start these 45 minutes plus subsequent question and answers concerning urban cableways. That seems a bit original, urban cableways. There are some cities that we will see shortly, which already have urban cableways. Some others are planning too, but let's start from the beginning and let's fix, first of all, our goals. The outline of today is a general introduction and history on cableways in general, then the ropes, their role and cableways, then why urban cableways, and their design. Sorry, just one. Fine, I'm back. So as regards the design, we will see just some first steps because, of course, in this available time, we cannot enter into the engineering and design of cableways, but I will provide you some first glimpses on how their design is done. So first of all, why should we look at urban cableways for sustainable mobility? First of all, the use of space. Our cities have difficulties sometimes to find more space, and anyway, the available space is usually, let's say, quite occupied by road vehicles. Then there is a question of safety because we had not this problem 1 century ago in the last decades, so as it is nowadays, though we have made some improvements in our cities in the last 2 decades, but road deaths remain one first cause or the first cause of death in our countries. So we have to look at that. Then a third element is hourly capacity, because if we look at the alternatives nowadays, if we put in standby for the time being the automated metros and conventional metros, which have very high capacities, but we need the demand for them, then if we go underneath 10,000 passengers per kilometer per, 10,000 passengers per hour per direction, then we have some alternatives, among which there are urban cableways. And then there is another issue that is how much fossil energy do we use and what are the consequences of local and global emissions. And again, urban cableways have an important role that we will see later on this. So we will see which are, first of all, in a more descriptive way, the urban cableways and the cableways in general, starting from their history, and then we will enter into more detail about their role in terms of space, safety, capacity, and energy and environmental impact. Let's start from a look. We know cableways for their use in sport activities, and we know a bit less probably their application, as we can see in this slide, for urban applications. But as we will see shortly, there is already a number. We will concentrate on this, of course. First of all, when cableways were born, because we have an history behind us, they were born more or less in the same period as railways. So in the first 2 decades of 2 centuries ago. In this context, in 2022, there was a first typologies, that is a freight rope installation that was built in Verona in Italy, but soon after in Vienna, then in Germany, then in Sweden, in the 20s and 30s of 2 centuries ago, some applications were born. In the second half of 2 centuries ago, some first Blondin installations dealing with freight transport, in particular of wood at those times, were installed in France. And then, starting from the 60s and 70s, we have seen the diffusion of cableways also for passenger transport. Then the first one was in 1866 in Switzerland. As you can see, all the main countries are Germany, Switzerland, Austria, France, and Italy, which were the places where cableways were born, and still conserve a strong competence on them. Then, as I was saying, in 2 centuries ago, and then mainly in the last centuries, in the first half, there was the diffusion of cableways for passenger transport, and also starting from the 20s of funiculars. That means those cableways which are operated typically either on rail or on air cushion. For example, in Zurich, there is a cableway for the airport operating on an air cushion with the traction assigned to the rope. Okay, then starting from the 80s, we have some first cableways that we will see later. This is an old company that you can see here, where the ropes were made. Now it's a bit more modern, the process, but we still need to know how the rope is made. We start from the steel, and then, as we will see later, we arrive to a rope itself. Then let's see a short history. These are the very first area ropeways for passengers of the 20s, 30s. On the bottom right, you can see a cableway in Turin, that is the city where I live, Politecnico di Torino, in Turin, of course. And it was reaching a hill in the surrounding parts, eastern surrounding part of Turin. But as you can see, there are a lot of aerial tramways already in the 20s and 30s, beside gondola ropeways. Then we had also some sledding on snow that allowed it to bring skiers on uphills. But there was already, as you can see on the left side, an urban cableway in the 30s. And some others arrived later. Then we arrived to the 40s, 50s, and 60s with cableways like this, typically on the mountains, and like these again in the 60s and the first 70s. More recently, in the 80s and 90s, we have some cableways like this, where we have two ropes, as we will see later, a carrying rope and a hauling rope, which have different roles in terms of strength and forces to be transmitted. And as you can see on the bottom left, there is a cableway in Germany. We have sometimes some possibilities to arrive to 1 kilometer, 1.5 kilometers, even 2 kilometers in a cableway done in France by an Italian company. But anyway, in France, it's 2 kilometers of difference of 8 in terms of position of the stations. So quite an important application. As we can see here, we have different kind of cableways that shortly we will analyze. Also the pulse, this one in the middle of the top of the slide is a pulse. That means you have groups of vehicles which are carried together to avoid the concentration of strengths in the same point of the rope. And now we arrive to urban cableways. So we have seen a short history, and we see some cableways operating in cities. On the top left, this is the urban cableways in Venice. It's a to and fro cableway that is represented on the bottom left of the slide. Then on the right side, on the top, you have the one operating in Zurich, in Switzerland, for the airport. The traction is assigned to a rope, but also you can see this one in the middle part of the right side of the slide, that is in Milan, for the conjunction of a metro system with a hospital, with a very high traffic. It's always full. I've been there more than once, and it's typically always full. And here on the bottom, there is the one in Perugia in Italy, that is an urban cableway too. But the main cableways in terms of numbers in the world are those that have been built recently in Latin America. As you can see here, you have Metro Cable in Medellin, you have Mexico Cable in Mexico City, Teleférico in La Paz, Bolivia, Transmi Cable in Bogota, and they have been increasing in the last 15 years. Typically, they are aerial ropeways with the concept of gondola ropeway. Of course, we are dealing with cities which have not a high level of historical buildings. I mean, they don't have to respect buildings of the 11th, 12th, 13th, 14th centuries. They are more recent, but they don't cost much. They avoid to go underground, and they can link in an easy way parts of the city. In a city like Medellin, they have, if they have not increased them recently, they have 8 gondola ropeways all connected together will satisfy a great part of the demand, and they have built their public transport on this concept. Consider that in the world, this is the representation of cableways for all the applications, of course, not just for the urban context, which are just a few for the time being. There are 16,000 in Europe, which is where cableways have been developed and are still the main core of the industry in this context, because there are 2 companies which are big, plus a few which are little, which have the 90% of the overall market in the world. So concentrated, very specific, but with an outreach at global level. In Asia, we have more or less 4,300 installations, many of which are in China, and then some others in the other parts. In Americas, there are only 1,400, but already some tens in the cities. The cableways typically involve a number of engineering areas. The ropes themselves in mechanical and civil engineering, the electric traction, the electronics, the mechanics, and the buildings. So they are typically a system engineering, they require a system engineering approach, with also some aspects in the architectural field for the stations, their insertion in the country or on the land, and the like. So let's start from the rope. Just a very short introduction. The rope is made by a core, then there are the wires around the core, and then the strands, which when they are spin around the core or the internal central wire, they constitute the rope itself. I don't enter into the, let's say, construction aspects, but you can have different kind of ropes of different construction, different diameters of the wires, and also with or without the core. It depends on their application. The core is useful for the flexibility and for the lubricants for the rope when it is in operation. But you can avoid it, you cannot have it when you have more rigid ropes, typically for allowing the load to go from one point to another one. We will see it later. Which are the main construction parameters? This is important because it will be part of the multiple choice test. So you need to know that for a rope, you need to know the diameter, the winding direction, so how these wires are winded, the strand pitch and winding angle, so the angle of the winding, the loss factor per spin, this is more specific, the minimum breaking load, this is important for calculating ropes and ropeways, the sum breaking load is a similar way for calculating the breaking load, the strength grade, that is the safety coefficient, the fill factor, which reveals how much part of the section of the rope is filled in with the metal, with the steel, the nominal mass per unit length that is necessary for calculating a rope weight, and the elastic modulus for the extension of the rope in different operational conditions, that is the weight, the temperature mainly. Okay, which kind of ropes do we have? A number, but the main element that you are asked to know are these elements, The carrying rope that is static. It brings the weight, but the weight goes along it. Then the hauling rope, that is the one which is moving. But if you have just one rope, that is a carrying hauling rope. It can be double, but is just one rope in terms of forces. That means that you have the weight and the traction together in the carrying hauling rope. You can have 2, of course, but they are 2 carrying hauling ropes. Okay? In the area ropeways, like to and fro area ropeways, you have the carrying rope on the top and the hauling rope on the bottom. The carrying rope is fixed and the other one allows the traction of the vehicles. Okay? Then, if you have to close a rope, you make the splicing. I don't enter into detail, but this is the way how you close in a unique ring a rope when you are dealing with a carrying rolling rope, typically, or with a hauling rope in the case. And you are dealing with a fixed rope when it's anchored, and this is typical of the carrying ropes. Okay, is there a normative, a technical standard? Yes, at European level, at the beginning of this century, there was a huge activities by the companies, by the operators, by the ministries for having a unique approach in the design, operation, maintenance of these installations. Also for some first urban applications, and this is made within CEN and the TC Technical Committee 242. Okay, there is a list of standards. I don't enter into detail, but I just want to let you know that each part of the standard, of the ropeway, of a cableway, is within a standard, related to a standard. So there is the terminology, the general requirements, the calculations, the ropes, the tensioning devices, the drive system, carriers, electrical parts, inspection, maintenance, operational inspection, recovery, evacuation, operation, quality assurance, all the components, all the kind of activities that you can carry on from engineering to maintenance and the normal operation are under the control of technical standards. And they are homogeneous because they have been agreed at European level. So let's see some applications in general terms, and then we will enter into those which are typically urban. What you see now is a funicular. It is very simple, typically you have the vehicle operating on railways, you have a drive station on the top, or at an extreme, if you are in a flat terrain, and then you have a hauling rope. Okay, typically, if it is a to and fro, you have a passing place at midpoint for crossing the vehicles. So you have just one rail, and you have this crossing in the middle. But we have a number of applications because we have the double monocable gondola, detachable. So you have the two ropes, as I said before, monocable, because it's just one function two function in the same rope, carrying and hauling. And you have two ropes, but it's a monocable, double monocable gondola. That is detachable. What does detachable mean? It means that when you arrive to the station, the vehicle doesn't continue to have the same speed of the rope, but it is detached. It can reduce the speed. It can allow to get in and outside the vehicle in safe conditions, and then it will be reaccelerated. This is necessary for urban applications, because while for ski resorts area you have people which are typically sportmen, sportwomen, who can enter and exit even walking and during the movement of the vehicle, this cannot be accepted in a city where you have, for example, a person on the wheelchair, or an old person, or a person with luggage. They have to enter and exit in safe conditions, so you need to stop. And this is strictly related to the detachable possibility. Possibility to detach in the station the vehicle from the rope. Then on the bottom right, you have a 3-cable gondola, but this is a B-cable installation with two carrying ropes and one hauling one. And here it is, the hauling rope and the carrying ropes. Okay. Then you can see a monocable gondola lift with fixed grips and pull set that I showed before, where you have groups of vehicles and you have a monocable installation with the towers along the line, as you can see, or a bicable gondola detachable. Again, when you arrive at the station, the vehicle is detached with an automatic grip for reducing the speed and then reaccelerating. Then here you have an aerial tramway. In the aerial tramway you have the carrying rope on the top, as I said before, the hauling rope on the bottom. The hauling rope is moved by the pulleys, the motor station, the drive station, and typically you have a to and fro movement. Consider that all these installations typically have an electric motor, so you don't have local pollution, and the power is concentrated in one station. So this means that you don't have to bring with you the motor like in typically all other transport systems. All systems for transport, all vehicles typically have an engine or an internal combustion engine or an electric motor on board. They have to bring with them the tank or the battery and the motor or the engine. Here it's different because we have the motor, an electric one, which is in a station. And then the movement is assigned to the rope or the ropes, which have a very low inertia. So from the energy point of view, this is the best solution. Not because I'm speaking about this, but this is the best solution because you don't bring with you masses that are engines, motors, tanks, batteries, and you assign that to the rope, which has a low inertia. So if you look at the energy consumption, as we will see later, this is the best option. Then this is a so-called funifor, which has, as you can see, the ropes. You have 2 + 2 ropes, and this is the most, I would say, complex solution. Okay, so having made this very short recall of the installations, let's concentrate on automatic people movers with cable traction, that is cable-driven APM. Typically, they can arrive to the maximum speed of the aerial ropeways that we have seen before, or the funiculars, which have 12 meters per second, and in the recent normatives, they have arrived to 14. You multiply by 3.6 and you have the kilometers per hour. So let's find an alternative transport mode for a city which has a so high speed. You don't find it. It's very difficult to find one. Well, you could have a bicycle which is very, very fast because it hasn't got any obstruction and could, of course, arrive to higher speed. But it's difficult to have so high a speed in a city. Okay. There are normatives, but there is only one guideline that was prepared in Italy a few years ago. That is the guidelines for the design of fully automated fully automated people transport system with rope traction. And they are the only one existing in the world, except a sort of standard by ASHE in the United States, which is very practical. It is not the more general approach that we typically have in Europe. Okay, where do we allocate these installations in terms of capacity? Around here. That means some kilometers, but you can create some sequence of them and a hourly capacity between 1,000 and 9, more or less, 1,000 passengers per hour per direction. And this is very competitive with respect to buses, with respect to tramways, with respect to conventional public transport. It's less than the automated metros that typically start from these values, 8-10,000 passengers per hour per direction. Okay, and let's see some applications. So here you see the first ones. In Laon, in France, this of the 80s, in Villepinte, again in France, then in Tampa, in United States. The one that you see on the bottom left part of this slide is again on air cushion, because it is suspended in the air and it has the traction that is assigned to the rope. Then this is the one operating in Zurich. I have shown before the part on the bottom right of the slide, but you can see the ropes, you can see the vehicle, and you can see also the air cushion here. These are students of mine that I brought to Zurich a few years ago when we had some more time to make technical visits outside the Politecnico di Torino for a couple of days. Okay. Given this, let's see our other applications, and then we will see the more technical parts. This is the one in Milan, which creates links between an underground with a park and ride area with an hospital, very used hospital. So you have thousands of people which each day go there. And this on the bottom is the one operating in Perugia, middle of Italy, and it is starting from a railway station and it arrives in the exact central point of the city, passing outside at the beginning, and then in a tunnel it enters into the city and arrives at the top of the city. Maybe you know that Perugia is on the top of a little mountain, a hill. Okay, so here you see the concept of the gondola ropeway that we have seen before. And this is the one operating in Venice, is a to and fro ropeway, the people mover. And here you see the Pisa mover for the airport of Pisa, from the center of the city, nearly the center of the railway station, and it links the airport. So you can arrive in a very short time from the center of the city to there. It has a length of just 1,760 meters with a capacity of 1,150 passengers per hour per direction. And the vehicle has the possibility to host 107 people. And here you see all those installations that are present in Latin America with their different roles and applications, but typically on the cities. Morelos, Mexico City, La Paz, Bogota, Medellin, that I mentioned before. And also these in Tolosa and Santo Domingo. So there is already a number of applications, and in particular in Latin America, this has been the increase of the installation of urban cableways. Consider that 15 years ago, there was a student of mine from Latin America, from Colombia, who came to Turin to study cableways and then went back to his country. And this is the development, not only for him, of course, but surely he has pushed a lot this development because now he's a leader in this context. And you can see that in 15 years, more than 30 cableways have been built. And now there are 3 or 4 under bid. So quite a great diffusion. And more recently, in 2033, both London and Paris decided to use a cableway. And so these are the applications for these important cities in Europe. Okay, there is also a possibility that is very recent to create an hybrid solution. What does this mean? Well, typically in the ropeways, you have the traction that is assigned to the rope. And as I said before, the engine, or the electric motor mainly, is in a station. But what about avoiding the possibility to reduce the speed and increase the speed, as we've seen before, in the station, without using all the electromechanical parts which allow this? You can assign it to the vehicle itself with 4 little electric motors and, of course, an energy carrier like a battery or cares or things like this, supercapacitors, that allow you to store some energy on the vehicle and then accelerate and decelerate by itself, then leaving the traction to the rope. This is an hybrid solution, and it has already been applied in Switzerland 2 years ago. These are the typical grips of this kind of ropeway. As you can see, there are some little electric motors on the grip that typically are not present because, as I said before, all is assigned to the rope. And this has been applied in Switzerland, as I said before, 2 years ago. So why should we adopt an urban cableway? Well, energy efficiency, environmental sustainability, safety, low costs when compared to equivalent alternatives which are equivalent in terms of hourly capacity, lower consumption of when you increase the capacity, and the low use of space. Here we can see some numbers. Well, if we take as comparison a BEV, a battery electric vehicle, typically it is around, that is the best option in terms of efficiency, not necessarily in terms of well-to-wheel. We spoke about that some lessons ago. So not necessarily from the overall energy point of view, but at the local level, at the vehicle, of course, you have an electric motor, which is very efficient. So we take that as an alternative, 0.11, 0.20, 25 kilowatt hour per vehicle kilometer. And a railway, 0.04 to 0.09 kilowatt hour per passenger kilometer. And the ropeway, 0.027 kilowatt hour per passenger kilometer along a section, but you can even have only 0.02 for the traction itself. Of course, we have different applications, different energy consumption, but this means that it's the best solution in terms of energy efficiency. What about space? A car typically implies 5 square meters per passenger and twice for the vehicle. Public transport, 4 or 5 passengers per square meter, that means 0.2, 0.25 square meters per passenger, and the bicycle 0.2. But a people mover is within a typical public transport. And so you have a higher capacity, but with the same occupation of the soil that, for example, a tramway or a bus has. So this is interesting because you have the same space use, but you double or you multiply by 3 for the hourly capacity. It's very interesting. And then what about the role of the cities? Maybe you know that 100 cities in Europe have declared their carbon neutrality goal by 2030. Among these, there is also Turin, and so we are quite involved by that. And here you can find the list of these cities. And as you can note, all of them have an important commitment in reducing the impact of urban mobility in terms of local pollution and global emissions. So in this context, they are quite related to the sustainable goals that regard in particular environment, pollution, and also safety. So let's take a look to the more engineering elements of an automated people mover. Is there a methodology? Well, the guidelines that I mentioned before provide a methodology, but let's see which are the main elements. First of all, an automated people mover is automated, so it doesn't require it doesn't require staff beside passengers in the stations and on the vehicles. Then it means that you have a control room, like for an automated metro, that controls all the line and all the vehicles with video cameras. From the procedural principles, we follow the typical approach of the design of a cableway, and there is some experience, not so diffused, but there is already some experience. Some pictures again of control rooms, the one in Zurich, the one in Milan, and this is of instead a funicular, so a more conventional ropeway. So what about engineering and design methodology? First of all, we have to define the plant layout. The plant layout is something that is related to the distances that we have to respect with reference to buildings, to the existing networks, and any obstacles that we have along the line. But from this point of view, the rope is very interesting because it's very flexible. So you don't have to respect the constraints that typically have rails, because rails do not allow you to have very, let's say, little radius, because you have to respect certain features of railway transport. Instead, in urban cableways, you can have some turns and adapt to the context, provided that from one point to the other, of course, the rope is straight. Well, the hauling rope is typically calculated as it is done for the other cableways, and little radius, as I was saying before, allow for some meters or very few tens of meters of radius. And from this point of view, this allows also to place the stations where you prefer, with a certain flexibility. Of course, so you have to guarantee the demand and a certain speed, so you cannot have each 100, 200 meters a station. You would have a distance that is typical of urban transport, 300, 400, 500 meters or even more. This is an example of viaduct. This example is taken in Milan, for example. And what we have to take a look at when we design, sorry, I go back, because we can have either in trench, so underneath the terrain, or in tunnel, but this would be very expensive. In trench could be affordable, or in a viaduct, or aerial, which is the most attractive in terms of use of space, because you don't use space except for the towers and the stations. So the aerial ropeway allows you to avoid the use of the soil. And from this point of view, we have to take a look at the environmental impact of these urban cableways. First of all, acoustic pollution. Well, we don't have any engine, we don't have any motor on board, so you have just a very low noise that is imperceptible from a certain distance, less than 30 decibel. That is very interesting. What about vibrations? Again, very, very low with respect to those provided by tramways and metros. Visual intrusion. This could be an obstacle because somebody says, well, in our historical city, I wouldn't like to see an aerial ropeway. But it's also true that if you have an aerial ropeway that is really aerial, so you have just the ropes, you have just a vehicle which passes when necessary. Then we have also some, let's say, very clever solutions, because I don't know if you have ever been in Japan, the bathrooms have glasses. I mean, you can see inside when they are empty, but when there is somebody inside the bathroom, the wind, the glasses, sorry, the door that is made of glass, it becomes dark. You cannot see anything inside. So the same can happen for cableways, because if they pass in front of buildings, then you cannot see inside the buildings. And this is a possibility. Then the possibility to insert in the existing urban context is very high, because, as I said before, it's very, very flexible and you have just to place the towers. And during the building, it's not so relevant in terms of impact as it can be for a traditional or a conventional metro system. I skip the individual impact because it's secondary in this case. What about the track line? As I said before, it can be in bank surface, in trench, in tunnel, or aerial. So, as regards these aspects, once you define how the vehicle is moved, then you can define how the wheels are made, in steel or with rubber. I mean, like a conventional wheel. And in case of steel, you have typically some components like this with an external wheel with double wheel flange, which operates as a guide, because the other one has to follow a certain path, while the left one can allow you to steer, to go to another path when needed. Then, as regards the alternative, it is typically in rubber wheels. There are a lot of urban applications with rubber wheels. Of course, when they are on the terrain, but if they are suspended, they don't need these rubbers. There are some applications with air cushion or EMS, but EMS, that is the electromagnetic suspension, is just theory for the time being. I've never seen them, notwithstanding that there are railway applications with electromagnetic suspension, and this is the base of hyperloop and magnetic levitation, with many discussions about them, but we will speak about this aspect in another seminar. The possibility in this kind of installation to have a turnable platform at the end of the circuit, where when you arrive at the end, can turn them, and this is quite interesting because they are little vehicles typically. What about evacuation and passenger recovery? Since we are dealing with urban application, we need some AIL for emergency, so an evacuation pavement with a certain width, and we need a staff, let's say, ready to help in case of need. But this is normal in cableways operating on mountains for ski resource areas. They operate in the same way. There are some people, skilled people, so staff, which leave work in the nearby, and in case of emergency, they go to intervene on the installation. Okay, this is a section of the pavement where the passengers can go in case of emergency. So the vehicle is open and they go outside, and they respond to certain standards. As regards the station, these are typical of civil engineering and architecture, and they have to respect some general criteria typical of automated metros. In fact, in this case, we rely on normatives on automated metros, with in particular the double doors where the vehicle arrives at the station. So there are the doors of the vehicle and the doors of the station, because you have to avoid the entrance of passengers on the line. Okay. This is an example of a station with line, and is taken from the case of Perugia. And the sliding doors, as I said before, are typical of automated metros. We have to avoid the piston effect, because if we are in a tunnel and the vehicle is arriving, like in metros, there is a compression of the air which would open the door. And there are some technical features to avoid this. This is the station in Zurich again. This is a model, well, a real scale model in Vipiteno, where there was a first test for the installation that was afterwards applied in Perugia. When you calculate these lines, you have to guarantee the appointment of a vehicle within a ring with the subsequent ring in case of to and fro systems, like in aerial ropeways. So you have to calculate the time on a ring, and this starts typically on the most extended ring. Then all the others will be adapted according to that. Because you will vary the speed in order to have the same vehicles on, I mean, when you have a vehicle which leaves a ring, it has to attach with the grip to the subsequent one. And so the runtime in all the stations, in all the sections, sorry, from one station to another has to be the same. Then, as regards the density, is the one that we have seen before. So 6 passengers per square meter, though we calculate them for 8, because we have to consider higher weights for any reason. If we look at some examples, the one in Milan that I mentioned before has something like 1,450 passengers per hour per direction, while the mini metro in Perugia has 3,600 passengers per hour per direction. Nowadays, we can arrive to 8,000 per hour, 8,000 passengers per hour per direction. This is an example of a rendering for a people mover. This is the vehicle operating in Cascinagobba that I mentioned before. And as regards the rope, we calculate it with some coefficients that are typical of cableways, typically around 4, that is the ratio between the braking force and the maximum traction that is applied to the rope itself during the operation. To do that we have to calculate it. And we have to consider also the wear and the acceleration, deceleration phases typically in a station. This is the one in Perugia. The grips have to be calculated too, with some references in the normatives, and we made some tests of resistance, and also on the rollers, because we have to avoid that the rope is detached, is, let's say, not pushed or pulled on the rollers. And this is typically calculated. Here you can see this rope has not to go outside the trace. If it goes, could happen in exceptional case, you need to place it again on the rollers. From the calculation point of view, this is a text in Italian. Impianti a fune means ropeways for passenger and materials. And typically we apply the catenary function, and we can calculate the rope in all the different conditions. Okay, and to do that, we have some instruments, software in particular, which allows for that. So we calculate the line. We use these guidelines that I mentioned before for following the main elements, and arrive to the conclusion before some questions. I've seen that there are 3, but I didn't read them. Typically, urban cableways are the most efficient in terms of energy. They don't create local pollution apart from very marginal aspects, and global emissions because they can rely on an electric power, on an electric motor, which can rely on renewables. So this is excellent from the environmental point of view. In terms of capacity, we are within 1,000, 4,000, but we can arrive to 8,000, 9,000 passengers per hour per direction, which is quite more than a tramway, quite more than a bus line, and it avoids 3, 4 lines of a road in terms of private motor vehicles. So it's very interesting. Of course, there is a visual impact, so it has to be accepted. And in terms of safety, I didn't speak about that, but the safest installation in the world in terms of transport are the automated metros and the cableways. If we look at the accidents, unfortunately, recently we had 3 accidents, important accidents in Europe, 14, 2, and other 11, something like that, people involved, but these were attributed to maintenance, not to the engineering and design, but to maintenance, lack of maintenance. So I'm concluding. I leave you some literature. Unfortunately, the book is in Italian, but there is some literature in English, and I leave the space for any question.